In writing Navier-Stokes equations, we have already assumed that the fluid is Newtonian and incompressible. Now we'll see what the equations look like and what are the implications of that when we have some more assumptions. For example, let's say the fluid can be considered to be inviscid, which means zero viscosity, or when the viscous effects are not there. It may happen that the entire fluid moves with the same velocity, also known as solid body motion or rigid body motion. In such a case, there won't be any relative motion between the fluid particles. Therefore, the effect of viscosity does not show up. So either it can be inviscid flow or a solid body or rigid body motion. Both of these situations are inviscid flow situations. So we are talking about inviscid flows. In such a case, if we have to write the Navier-Stokes equations, let us write the Navier-Stokes equations first of all. We'll write the dimensional form rho. I will not expand the left hand side for now. I can write rho dV by dt equal to minus grad P plus mu del square V plus rho G. Okay. If we know that gravity acts in a certain direction, we can write this rho G. Let's say the gravity is acting in the negative Z direction. Then we can write it as minus rho G, which is a scalar, the value of the gravitational acceleration, and k cap. So minus k cap is the direction in which this gravitational acceleration is acting, or gravitational force is acting, and G is the magnitude of that acceleration. Alright. Now if the flow is inviscid, which means the viscosity is zero or viscous stresses are zero, or there are no gradients in velocity, either of those things, then this term can be neglected, okay, because it is inviscid flow. Then you can write rho dV by dt minus del P plus rho G, or let me write minus rho G k cap, if I know that gravity is acting in this direction, okay, which is the minus Z direction. All right. These equations I am saying because this is not a single equation, there are three equations here. Because this is a vector equation, you can see velocity has three components, grad P has three components, and minus rho G, the two components in the x and y directions are zero. There is only a third component of this term which is in the k direction, Z direction. Now these equations are known as Euler equations or Euler's equations, which is for an inviscid case, and these are valid in many applications actually, even when there is some viscosity to the fluid, which is the practical case, because every fluid has certain viscosity and not everywhere will you see a rigid body motion in a fluid. There will be some relative motion between the particles, but still you can apply these equations, the Euler equations, because the viscosity is so negligible in certain cases that you can neglect this term altogether. Okay. Now um, there is uh, a formula that we can derive from this equation, these equations, which is known as Bernoulli's equation. We'll derive this, but first of all we have to see what this Bernoulli's equation says. So you might have read this in your school as well. So there, as I remember it, there they talk about energy and work, and say how a certain form of energy converts to some other form of energy or work. So they consider a pipe like this with varying cross-sectional area, with varying elevation. So here, let's say this is Z1, here this is Z2, and there is gravitational force acting, and you have some reference plane from which you measure these Z1, Z2 and any other Z in between, let's say. And you can write this Bernoulli's equation in terms of energy contained in the fluid element at a certain cross section and at some other cross section. Okay, so if you write the energy conservation equation between these 2 points 1 and 2, you will get the Bernoulli's equation. But that can also be derived from this Euler's equation. Here what we'll do is, so here when you derive it from the energy point of view, there certain things are not so explicit, not so explicitly clear, such as the Bernoulli's equation tells you the relationship between these 2 points only along a streamline. What is a streamline? We have already discussed that when we discussed path lines, streak lines, and so on. So if this is a streamline is at a instantaneous point of time, and on a streamline, if you draw velocity vectors, you'll find that they are tangential to this line. Okay, so such a line is known as streamline, on which the velocity vectors are tangential at that point of time. And the streamline can change at a later point of time if the flow is unsteady, it is not fixed. But if a flow is steady, then a streamline does not change. Okay, it remains the same, and both path line and streak lines are same as the streamlines for a steady flow. So Bernoulli's equation is also valid only for a steady flow. So these are the assumptions here. The flow has to be steady. We have already derived these Euler equations using the assumption that this is an incompressible flow. Okay, here one more thing. We have del dot U or del dot V equal to 0 for incompressible flow. So this equation has to be solved along with the momentum equation. Only then do you have a complete set of equations which you can solve to get a solution. Otherwise, we don't have sufficient number of equations if we don't include the continuity equation. And we have assumed that this is an incompressible flow. So Bernoulli's equation also, you have these assumptions. This is an additional assumption that the flow should be steady. The third is that there should not be any viscosity to the flow, or it should be frictionless. Either it can be a rigid body motion where there is no friction between any two layers of the fluid, or any two regions of the fluid. So the third I can say is inviscid flow, where 2 and 3 we have already taken care of in Euler equations. And the fourth is that the flow should be along a streamline. So these two additional assumptions, that it has to be steady flow and the flow should be along a streamline. If there is a flow in which let's say the streamlines look like this can easily happen in pipe flows. Let's say you have a pipeline like this and a second pipe is joined like this. Then you have a streamline which goes like this and a streamline which comes like that and joins here. Okay, this is one of the streamlines. Or it can be that the streamline is going like this. Then in this case, if you want to apply Bernoulli's equation between a point here, let's say point number 1, and a point 2 here, you cannot do that. Okay, because this is not a single streamline which you are talking about. You can apply Bernoulli's equation along one of these streamlines, for example a point here and a point here. You can apply the Bernoulli's equation between these 2 points, or between a point here and a point here. You can apply Bernoulli's equation between these 2 points, but not between these 2 points 1 and 2. Okay, so how do we derive Bernoulli's equation? Let us see. First of all, this is a steady flow, so there is no time term here. Let us drop the time term from these equations. We get, let me write it in Cartesian coordinates or rectangular coordinates. So this is, okay, let me just expand dv by dt for clarity. dv by dt can be written as dou v by dou t plus v dot del v okay, which can be written as u dot so first will be u dou by dou x. Let me just write the entire thing here, plus v dou by dou y plus w dou by dou z. This is the operator which acts on v, which is ui plus vj plus wk cap. Okay, now we'll not be using this expanded form here. We'll just write rho times v dot del v. This is equal to minus del p minus rho g k cap. Here we have rho common in the left hand side and on the second term on the right hand side. So let us divide by rho. We get v dot del v equal to minus del p by rho minus g k cap. Now in this derivation, although we are taking gravity in the minus z direction, but it doesn't have to be the case. It can be in any other direction. It can be I cap or j cap or any mixed direction also. That doesn't change the result. Okay. Now what we'll do is, let us assume that there is a streamline like this, and let us choose an element here. This is a small element, infinitesimally small, but I am showing it as a big line segment here. Okay, let us call this ds, and it is a vector in the direction of velocity. Alright, so ds is a vector in that direction. And if we see the components of this ds in x, y and z directions, we can take these components and call them dx, dy and dz. Thus ds can be written as dx I cap, dy j cap, dz k cap. Alright, this is along this streamline S. If you call this streamline S, although it is not a vector, at every point it has a different direction. So this is just a naming convention that we are using. This is S, and ds is a vector. At that instant, whatever is the direction of velocity, that is the direction of ds. Okay, now what we'll do is, we will take a dot product with ds of this equation on both the sides. What we get from here is, let us see this pressure term first, what we get from there, because this left hand side is a little bit complicated. Let us see what the pressure term gives us. Let us expand this. We have minus 1 by rho dou p by dou x I cap, dou p by dou y j cap, dou z k cap. And the dot product with ds, ds also we can expand in terms of dx, dy and dz k cap. Okay, so from here we get dou p by dou x dx plus dou p by dou y dy plus dou p by dou z dz, which is equal to dp. Alright, which is the total derivative, or dp by dx times you can say dx, or dp by ds times ds, something like that. So this is the definition of total derivative. So we get minus dp by rho. So what we did here was minus del p by rho dot ds, which gave us minus dp by rho. Now let us find out the dot product with the second term on the right hand side, which is the gravitational acceleration term. So that is minus g k cap. Let me write it here so that it is clear. Dot ds is equal to that. Similarly, minus g k cap dot ds, we can write it as minus g k cap dot dx I cap plus dy j cap plus dz k cap. So here you can see that the first two terms, dx I cap, dy j cap, they don't have any matching component here in the gravitational acceleration term. We will get minus g dz. Alright, Now what about the left hand side, which is v dot del v dot ds? There is a vector identity from which we know that this is equal to half del v dot v minus v cross del cross v dot ds. Okay, and after solving this I can write all the steps here, but okay, let me write it. This is also given in the textbook that we are following, Robert Fox, Introduction to Fluid Mechanics. So this becomes half del v dot v dot ds minus the second term v cross del cross v dot ds. Okay, and now here we know that the velocity vector and ds are in the same direction. Therefore this term goes to 0 and the remaining term, that can be written as v dot v dot ds, which is equal to dot ds. Okay, so from here we get that this is equal to d v square by following a similar procedure what we followed with pressure term. Okay, in the pressure term we had del p dot ds, here we have del of v square dot ds, where v square is a scalar. All right, so we get half d of v square, that is the differential, total differential. So if we combine all these three terms, we get dp by rho plus half dv square plus g dz equal to 0. And we have to note that this is along the streamline S that we have done this. We have taken a dot product with ds here. So we are going a distance ds and we are calculating these derivatives dp, dv square and dz in that displacement ds along the streamline S. So these derivatives dp, dv square, dz, these are not arbitrary differentials in any direction. These have to be taken along the streamline S. All right. Now, so we can write in the bracket, this is along S, along the streamline S. Now we'll integrate this equation on both sides. The first term will get an integral like this, second term and the third term. So the first term, because rho can be a function of pressure or pressure can be a function of density in some cases, we'll leave it as it is, dp by rho, and we'll write here what is dv square, which it is v square, and you have 2 here, And what is integral dz? G is a constant, so this becomes gz. This is equal to 0 along the streamline S. Now if density is a constant density fluid, then we can write it as dp by rho. So dp integral will be p, and by rho plus v square by 2 plus gz equal to, and it was not 0, you'll have to integrate this 0 also, so this becomes a constant equal to c, we can say, and this has to be along a streamline. Now some people also write this as p plus rho v square by 2 plus rho gz equal to some other constant c1, because density is anyway constant here. So both of these formulae are fine. So this is known as the Bernoulli's equation or Bernoulli equation. Okay. Now some applications of this we can talk about. For example, let's say there is a converging section. This is a solid and this is also a solid. It can be conical or it can be two flat walls. And let's say there is a flow like this. Now let us consider this central streamline which is going like this. And let us consider 2 points here, 1 and 2. Now from the continuity equation, we know that what will be the relationship between the velocities at point 1 and 2. What will be the relationship between the velocities? So you can say that a1 yes. So continuity equation, let us write that a1 v1 equal to a2 v2, which says that area of cross section at point 1 times the velocity at point 1 is equal to area of cross section at point 2 times velocity at point 2. That is the mass conservation or volume conservation in case of incompressible fluids. So here we can see that velocity at point 1, area of cross section at point 1 is more than area of cross section at point 2. Therefore velocity at point 1 should be less than velocity at point 2. The fluid is accelerating as it goes to point 2. Now what does the Bernoulli equation say about pressure? So let's say you are designing this nozzle or these parallel plates. Where will the pressure on the walls be felt more? At point 1, so at this cross section or at this cross section? So to see that, let us see the Bernoulli's equation. If you see this streamline, along this streamline, the Z elevation from a reference plane is not changing. Therefore, we can write P1 plus rho V1 square by 2 plus rho G Z1 is equal to P2 plus rho V2 square by 2 plus rho G Z2, which is same as Z1, so these two cancel out. Alright, let me write it as Z2, and Z1 is equal to Z2. Even if there is gravity in this direction. Okay, so no matter what is flowing here, water, air, any other fluid which is heavy. If the streamline is parallel to the ground, there are no elevation changes. Now let us see what the other terms say. So V1 is less than V2, therefore this term is less than the term on the right hand side, the velocity term. Therefore P2 has to be higher than P1 to balance the equation. So let us write P1 has to be higher because V1 is less. P1 should be more than P2. Okay. So the static pressure in the fluid P1 will be more than P2. So the pressure that is felt here at this cross section, actually we are talking about this point, but if we consider a streamline like that, then we can talk about pressure close to the wall as well. And if you see that streamline, there are some elevation changes, but if it is a flow of air, then we can neglect those elevation changes as well, because this rho g z1 and rho g z2, these are very small terms as compared to the other terms in the equation, if the density is small enough. Okay. So for this central streamline, we can say that pressure at 1 should be more than pressure at 2. Okay. Now you would have also read about flow over an airfoil, which we talked about some time back. So if the shape is slightly asymmetric, or the airfoil itself is symmetric but it is tilted with respect to the flow direction, then from Bernoulli's equation you can see that because the air is actually stationary and the wing is flying through the air, the velocity of air in the front of the wing and at the back of the wing, far away from the wing of course, and if the flow is laminar, the velocity of air is same, right, with respect to the wing, because actually the air is stationary in front of the wing and at the back of the wing, far away from the wing of course. So we cannot apply just after the wing, we cannot apply the Bernoulli's equation. But still, in a situation where the flow is laminar and you don't have much change in the flow after the wing, then you can say that the air velocity is same in front of the wing and at the back of the wing. Therefore V, this is same, and because of the shape of the wing, or if you consider this top wing and look at the streamline, the air at the top has to travel more than the air at the bottom. Therefore the velocity at the top has to be more than the velocity at the bottom of the wing. Okay. And in this case also you can see something like that. So the velocity at the top, let me write V top, is more than velocity at the bottom of the wing, and you can consider 2 points, let's say a point here, point number 1, and point number 2 here, and you can consider other 2 points, point number 3 and point number 4. You can apply Bernoulli's equation between point 1 and 2. So you can write P1 plus rho V1 square by 2, and let us neglect the changes because of gravity. Let's say those are negligible here. So let's write P1 plus rho V1 square by 2 is equal to P2 plus rho V2 square by 2. Now uh, velocities are same, so we know that pressures are also same at all of these points 1, 2, 3 and 4. Pressures should be same because velocities are same at points 1 and 3 and 2 and 4. Okay, so pressure here is same as pressure here because velocities here and velocities there are equal. Now let us talk about a point here. Let's call it point number 5, and a point here, point number 6. Let us write the Bernoulli's equation between point 1, 5 and 3, 6, which is same as applying Bernoulli's equation between point 5 and 6. Although the streamlines are different, but we can do that because we can write P1 plus rho V1 square by 2 equal to P2 plus rho V2 square by 2 equal to P5 plus rho V5 square by 2. We can write this because that is a single streamline, and for point 3, 4 and 6 we can write the same equation again. And we know that for point 1 and 3 pressure and velocities are same, therefore we can write this equation for point 1 and 3 also, which tells us that we can write it for point 6 also in the same line, P6 plus rho V6 square by 2. Okay, so although we have considered different streamlines, we can do this because the constant on the right hand side is same for both the streamlines here. We have deduced this from the flow configuration, from the kind of flow that we are seeing here. So if we consider now these two equations alone, we get a relationship between the pressures and velocities on top of the wing and bottom of the wing. So as we discussed, velocity at the top has to be more than the velocity at the bottom. So velocity at point 6 is higher and this is lower. Therefore, to balance the equation, velocity at point 6 should be less than velocity at point 5. Therefore, we conclude that pressure at point 5 or pressure at bottom is more than pressure at the top in such a case, in this kind of an airfoil. If the airfoil was bent the other way, like that, then it will be opposite, because the velocity at the bottom will be now more than the velocity at the top. Therefore, now the pressure at the top will be more than the pressure at the bottom. But let us discuss this case for now, which is the case for an airplane. The wings are bent like that. So let us draw it again here and see what pressure it gives, what forces it gives. So pressure at the bottom, let us draw it with big arrows, and pressure at the top with small arrows, just to show the difference. Pressure at the bottom is more. So if you integrate the pressure applied by the fluid on the wing on the entire bottom surface area, then you get a force. Okay, force at the bottom, which will be more than force at the top, the mod of course, because force is a vector. Now which gives you a net upward force in this case, which is known as the lift force. Okay, and this is how the shape of the airfoil gives a lift to the airplane when it is flying in the air. So there has to be some incoming velocity. Only then you will have some difference between the top and the bottom velocities, because the air has to flow. And the difference also depends on the inlet velocity magnitude. The larger the inlet velocity magnitude, the larger the difference between the top velocity and the bottom velocity. And the larger will be the lift force. So it depends on the speed of the airplane as well, how much lift you will generate, and the shape of the airfoil. So if some of you have traveled by a flight, you would have noticed that they tilt this airfoil, this shape, they tilt the wings while taking off and while landing. While landing, they may even invert it so that there is a force acting downwards. Okay. And nowadays actually they don't have the entire wing that tilts. They have a fixed wing like this, and they have a small tail which can tilt. Okay, and that does the same thing. So if it is tilted up, you can see that it will be curved like that, the streamlines will be curved like that, and if it is tilted downwards, the streamlines will be tilted like that. Okay, thus generating different forces on the wing. In the blue case, it will have a positive lift, and in the red case, red streamlines that I have drawn, it will have a negative lift. Alright, so this is about Bernoulli's equation. We'll discuss some more problems on Bernoulli's equation in the next live class. Thank you.